Okay, so more on rotational motion. There are a number of ways to think about this. Here are just a couple that might help you. So when I imagine rotational motion, I always sort of think about an object in the XY plane. So I try to think about, put my X, Y, my position up here, and then I think about something moving at a constant radius, okay? And so we think about an object, maybe it's right here. Its displacement vector looks like this. And so now I think about something moving in the XY plane. So at any given time, maybe it has some angle theta, but it may be, that object may be moving. It may be accelerating. These are the types of ideas that you want to put together yourself, all right? Now, when something moves at a constant angular rate or with a constant angular acceleration, there's an analogy to all the work that we've done already with linear motion. That may not be entirely clear, but as you're doing this, try to think about a correspondence between the translational quantities and the rotational quantities. So in the translational quantity, we think about usually x or y, the x position or the height. But the rotational analog is the angle theta, an angular position. We've thought about the velocity. When you think about the velocity, I want you to think about omega, which is the angular velocity, right? So just like the velocity tells us how x or y changes with time, omega tells us how theta changes with time. Similarly, we've talked about acceleration, and the rotational analog is alpha. That's an alpha. It's a Greek alpha. And it's the angular acceleration, how rapidly omega is changing with time. Okay? So these are these equations that we developed. On the left, these are all the translational kinematics equations. Okay? Now, if you're having a hard time keeping all this stuff straight in your mind, write these down or have this cheat sheet ready for you. But you'll see that there are very similar forms for the rotational kinematics equations and the translational ones. You just have to remember sort of the analogs. Spend some time with this, okay? Don't rush through it. It's very tricky, okay? We're going to imagine, oftentimes, objects that are rotating. Okay? And don't forget that when things move together, okay, everything rotates at the same rate. All right? So for instance, we might have maybe a wheel spinning, right? Okay? So what I like to think about when I try to develop an idea in rotational motion is I have a point on a wheel. And if you look, try to put them at roughly the same spot here. Look at this blue dot compared to the position, right? So what I can do is I can imagine moving it around, moving it around, moving it around, moving it around, moving it around. Okay? And let's pretend like that dot's traveling around at constant angular rate. Okay? Now there's a convention for the direction. Now the direction's not intuitive, okay? We use the right-hand rule. Okay? So in this case, I am spinning the dot so that it's rotating kind of in this sense, okay? Now to you, that would be, what is that? Counterclockwise, I think? I think so, okay? Counterclockwise. So if I wrap my four fingers, if I wrap in the sense, my thumb points in the direction of the angular velocity, all right? Now that's towards you. This slide reinforces that, I hope, okay? So here we have a disc rotating, and so what you try to do is you try to wrap your fingers kind of as that arrow that wraps around the object. So it's spinning about the axis, okay? So your thumb points in the direction of the angular velocity vector, right? Vector. Okay, so we call this the right-hand rule. All right. So we're going to think about objects that are rotating, objects that have an angular velocity, and objects that have some angular acceleration. Okay? Now, we're also introducing the idea of torque. Okay? When I think about torque, I think about closing doors. Okay? So in order to close a door, I need to apply force. Well, there are many ways that I can apply that force. All right? So, do a demo. Take a door and try to close it. Okay? Try to push it in different ways. And I think what you'll find is that you have to push with a little bit of force, at least, normal to the door handle. Okay? You can't pull on the door handle in such a fashion that you can't close the door. That's a conceptual idea of torque. Okay? So let me sort of sketch out what I mean here. Okay? This is my door. Okay? This is my hinge here. All right? So if I want to try to close the door, let's say that closing the door would be to put it vertical. Well, I have to apply force in a specific way. I can't apply a force like that, right? That wouldn't close the door. I have to have some component of my force that points in this direction. All right? So that's the key idea behind this torque thing. Okay? So torque is force at a distance. Okay? In this case, we pick a rotation axis. I encourage you to find one that's intuitive, but the hinge, I think, is a pretty intuitive one. So I want to measure the torque exerted by this force about the hinge. So I draw a vector r that points from the hinge to where I apply the force. So that's r. Okay? From the rotation axis to where I apply the force. And the torque, due to this force F, is in magnitude, it's going to be the distance r, and the component of the force that's perpendicular to r. Right? So if I have a force that's sort of off at some angle, then I have to find the component that's perpendicular. So I drop a perpendicular, and that's going to be this, going to be that length there. So pause the video if you need to see that. But I need a component of my force perpendicular to the displacement r. This is a slide that goes through that idea. Again, there's a lot on this slide, so take your time. Key points here, though, are that if I'm pulling straight out of the pivot, that's phi is equal to 0 degrees, the torque is 0. Also, I could push radially. That would be phi is equal to 180 degrees. And again, I get 0 torque. Now, from this picture, you can also see that I can put point phi so that I can apply torques in different directions. All right, so we have a phi of plus 90 degrees and a phi of minus. When you look at this, these are the same. There's the same directionality associated with the right-hand rule that we can get from torques. That is, torques can cause angular accelerations. Those torques can be positive or negative depending on the right-hand rule. This may be difficult. Challenge yourself. Okay, we're going to do some work in class, which I think will be helpful. But torque can be a new idea. Okay, so try to find intuitive physical situations, loosening bolts, opening doors, rotating merry-go-rounds, whatever it might be, to try to make a physical connection to the concepts. Okay, but if you need any help with this, make sure that you come and chat with me.